Hello everyone, welcome to our presentation for the paper Modular Building Connections, a review. This is a conference paper that is coming from a journal paper, and we have presented there much more information if you want to go and see it at the end. My name is Konstantinos Daniel Tsabdaridis. I'm a professor of structural engineering at City University of London, and the work is predominantly done by Mr. Kaur Fars, PhD at City University in London. Now let's go a little bit about the background of these connections. Where are they used? So modular building systems, also known as MBS, are a form of a modern method of construction, also called MMC, which adopts principles of off-site manufacturing and off-site construction, delivering ready-to-install, fully finished structural modules. Main advantages of MBSs are that they are producing reduced manufacturing cost due to the standardization and mass production, speed of on-site construction guaranteed by the straightforward assembly sequences, and superior end products delivered by better quality control and improved accuracy of production lines. Now, while we are doing this review, what is the main challenge? The problem is that the last years, I would say around 5 to 10 years, there is a large sheer volume of newly proposed connections, and in particular intermodular connections that are presented by researchers, and some of them are also coming from different fabricators. There is also a good number of review papers that have partially covered the literature review of such connections, often being inconsistent though. Consequently, the aim of the present study is to provide a harmonized overview of the existing literature by proposing a unified nomenclature and a systematic classification based on the method of joining. The main outcomes of this work is the consistent classification and the unified naming convention, is the scalable classification system, which will help engineers and researchers to adopt those connections and use them, and of course further expand in the future by adding more connections or more systems, as well as the key areas of improvement revealed by this multi-attribute ranking system. So again, it helps with the decision making. The literature of intermodular connections for hot-rolled steel MBSs was systematically reorganized herein and drawing attention to the key features of these systems. The connections were classified and labeled under the following categories. We have the connections with locking devices, we have the ones that they have post-tension members and rods, and we have the bolted connections, and because there are quite a lot of them, we categorize them in column to column, beam to beam, as well as fitting to fitting connections. First category of the locking devices, connections with locking devices, 7 innovative connections were identified, and these joints used either tool-driven or gravity-actioned mechanisms. First one is a twist lock, then you have these interlocking grooves. The third one is a rotary device and screwed nut, self-locking plug-in device, a torque-activated pin device. The last two are self-locking spring-activated tabs, and the last one, I believe it is with sliding blocks. So you can see that these are kind of mechanical connections where there is either a tool or a kind of a device that is creating that interlocking system. Quite sophisticated and very interesting to explore more. In the second category, we have the Posttension PT interlocking connections, which consist of rods inserted through hollow sections, which are continuously through the full length of columns. When necessary, bar continuity was ensured by couplers or sleeve nuts, while nuts tightened the rods to connecting plates, which could also enhance the shear force transferring by various types of shear keys. We identified 6 of these connections, and you can see they all have rods passing through the middle of the sections. They are enhancing a lot the tensile capacity, the tension of these volumetric systems. So if we are having, for instance, tall buildings and they're subjected to lateral drifts and there is a lot of tension force, these cables, they're holding all the volumetrics down. Last category are the bolted connections, which are the most diverse, using common, easy to manufacture steel parts such as corner fittings, plates, bolts, screws, nuts, washers, and other components like pins, tenons, pivots, and rubber layers. So these are more advanced. Starting with the column-to-column CTC intermodular connections, which are derived from classic splice joints for tubular sections with plates, which are welded to ends of the hollow sections and clamped together by bolts. We've identified 16 different versions. Some of them are pretty simple, like 01, 02, 07, 8, 9, 10, and 12. The others are a bit more advanced, using more components and access holes. Again, worth noting that most of the bolts here are vertical, a part of that one in most of the others. 01 is a vertical and horizontal plates, 02 up-down beams, 03 cover plate with blind bolts, 04 bonded sleeve splice joint, 05 connecting plate and access holes, 06 extended connection plate, 07 bolted intermediate plate, 08 overlaying extended end plates, 09 intermediate plates and interior bolts, 10 is got a cruciform plate, number 11 interlocking pins and connecting plates, number 12 connecting plates and resilient layers, number 13 is quite difficult to see here. It's got an inbuilt tenon and side plates. Number 14, which is very interesting, is got a shape memory alloy bolts. Number 15 is got guiding tenons and internal sleeve pipes, and number 16 is interconnecting tube and nuts. The next one is beam-to-beam connections, which are made of gusset plates of various geometries, engineered to closely fill the gaps between modules and optimizing the unusable space between each of the floor and ceiling cassettes. Here we see different types of connections. We have bolts in horizontal as well as vertical directions. BT01 is a cruciform plate, BT02 is a connector plate, BT03 is a gusset plate that is used, 04 bolted intermediate tenon plates, 5 cruciform socket shaped tenon, 06 is a plug-in tenon device, 07 is interpenetrating tenon devices, 08 is a cross-shaped plug-in connector, 09 is a plug-in bolted adapter with spring pins, number 10 is a bolted gusset plates, number 11 is using plug-in tenon and high-strength and blind bolts, number 12 is bolted PFC double beam. So we see that they vary quite a lot. The most interesting thing here is that this kind of intermodular connections is more appropriate for component-based modular construction rather than volumetric-based. The third category under the bolted joints is the fitting-to-fitting FTF connections, which stems from the common feature of engaging modules through corner fittings. The shape of these cast corners ranges from the classic ISO design adopted from shipping containers to more refined and computationally optimized typologies. We've identified 19 different FTFs, starting with the first one, which is steel hollow cube bracket, and the second one an intermediate plate. The third one is got gusset plates and locating pins. Number 4 is got tie plates and spigots. Number 5, tie plates and twist locks. Number 6, rubber isolator and steel clamps. Number 7 is a transverse clamp. Number 8, cross-shaped clamp. 9 is X-shaped clamp. Number 10 is bolted corner fittings. 11, square pipe blocks with internal circular pipes. Number 12, gusset plates and locating pins. Number 13, bolted corner fittings. Number 14, vertical bolts through columns. Number 15, corner fittings with internal threaded aperture. Number 16, corner fittings with rubber isolation, and that's one of the connections that we're studying quite a lot in our group. Number 17, bolted end plates and intermediate plates. Number 18, external bolts and positioning plates. Positioning plates are used quite a lot. And number 19, cruciform plate and horizontal bolts. After this extensive literature review, we developed a multi-attribute ranking system for the intermodular connections for hot-formed modular building systems. The scoring system was based on 3 core criteria: the structural, manufacturing, and constructional performance attributes. In the lack of consistent quantitative data that we were getting from different papers and review works, a qualitative approach was based on visual inspection combined with engineering knowledge and intuition was adopted for the characterization of the connection systems. It is worth noting that having about 60 different connections, we have a very good sample, and we believe that our ranking is pretty accurate and reliable. Through the scoring metrics proposed herein, a practical, comprehensive, and scalable multi-attribute ranking system was achieved, which could be used in order to help researchers as well as practice engineers as a decision-making tool. Metrics for the structural were the vertical and horizontal connectivity, the ability to provide both vertical and horizontal load paths, the design resilience, in other words, the ability to mitigate or completely avoid permanent damage in the members of modules, and the design flexibility, in other words, how easy it is to adapt or scale connection configurations for more than just one application. In terms of the constructional attributes, the metrics were the design for assembly, the DFA, as it is well known, which is a practical and accessible joining operations that require low to moderate human intervention. The design for disassembly, DFD, the ability to allow fast and intuitive reverse engineering, and the tolerance control, TC, which is the ability to accommodate built-up or construction tolerances without jeopardizing the aesthetics and the structural integrity. In terms of manufacturing, joining complexity, JC, it's the level of detail and regularity of the connection. Easy to integration, EI, complexity of in-shop fabrication and processes required for delivering the final connection part. And the ease of pre-assembly, EP, which is the complexity of required in-shop assembly procedures. The proposed multi-attribute ranking presented here was used to determine the highest scoring the connections for each performance category, revealing the most promising per attribute as well as the best performing system for each type of connection. The discussion focused on the highest overall scoring, so how the bar is added with all the scores together, and their bespoke characteristics, while complete data plots scoring methods for each metric are available in the full review journal paper. Here you can see the synopsis of the results with the 8 best performing connections. The highest scoring systems were the FTF06 and FTF11 joints with totals of 21 points each. The FTF06 scored best in metrics such as DR, DF, DFD, and TC due to its flexible, resilient, and demountable configurations. The only improvements could be reducing the number of bolts, which require on-site tensioning, while manufacturing complexity of the lead rubber bearing may be mitigated by using a high damping rubber bearing instead. The next 4 joints were the FTF 19, 12, 03 and BTB 09, coming second with totals of 20 points. These joints displayed well-balanced scores for all metrics, demonstrating robust joints which could be improved in terms of resilience, reuse opportunities, or complexity of fabrication. And the next 2 connections scored 19 points, each achieving medium scores in almost all metrics. The CTC 11 system highlighted the efficiency of common and easy to manufacture features such as interlocking pins and bolted end plates, while adding means of energy dissipation and damage control would help improving its resilience and demountability. Connection CTC12 had an efficient configuration made of common parts with good energy dissipation provided by the rubber layers, yet the inclusion of self-aligning features and mitigating the difficulties in repairing or replacing the damaged end plates after an earthquake could be considered for improving its structural and constructional metrics. In the end, it must be noted that the purpose of the ranking discussed above was not to suggest that one connection would be better than all the others, as there is no fit-for-all solution in multidimensional problems like this one. As the discussion demonstrates, the proposed framework is useful in revealing key features which make efficient designs, both in terms of structural, constructional, and manufacturing aspects, while it also uncovers areas which require improvement, serving as a good starting point for future research directions. So the concluding remarks of this comprehensive literature review study, with the classification and the further multi-attribute systems that it was developed, are that this study provided a harmonized overview, first time, of the relevant literature, having reviewed, classified, and indexed 60 connections using a unified nomenclature and a systematic and consistent classification system based on joint typology. A new multi-attribute ranking method was developed using a qualitative approach which can facilitate future designs as well as enhance existing connections in low-scoring areas, serving as a useful decision-making tool for both researchers and practitioners. The multi-attribute ranking system revealed that the use of corner fittings, bolted joints, self-aligning or locating parts, and damage control devices were all must-have features for connections with all-round performance, so we suggest them to be added in most of the connections. And finally, more focus should be put on addressing the hindered demountability and reuse operations caused by the lack of seismic resilience. It's a topic that is extremely interesting for us in our 3D MBC group. So if you want to know more about that and what we are working on, please visit our website, as you can see at the top right corner. Before I close this presentation, I would like to warmly invite you to submit your contributions, such as research papers, review articles, technical notes, or other kind of papers, to our two special issues that are part of the 3D MBC interval. First one is called Innovative Structures and Materials, Analysis, Design and Applications, and you can see below the topics that are covered. Anything that deals with new type of structural systems is very welcome. The second special issue is the application of additive manufacturing in construction. This is again a special issue that covers anything around 3D printing. It can be on metals, on polymers, on concrete, different materials. It can deal with structural applications. Both these special issues, they have a deadline by the last day of 2022, 31st of December 2022. So you can scan the QR on the bottom right and you can get to the journal directly and you can submit your contributions. If you want to have a chat about your paper, feel free to reach me. I'm a member of the editorial board. I must say that Buildings is a journal that is gaining a lot of traction the last few years, and its impact factor is improving very rapidly, and a lot of renowned academics belong to the editorial board. So feel free to get in contact and submit your papers. Thank you very much.